and A multi-determines C, then we have A multi-determines B intersects C. The transitive rule is slightly different from exact transitivity. What it says is if we have A multi-determines B and we have B multi-determines C, then we have A multi-determines not C exactly, but C minus B. And you might work some examples to convince yourself why we don't have just A multi-determines C and we have to subtract the attributes for B, although it's fairly complicated. So again, these rules can be proven, and there are many other rules for multivalued dependencies that you could read about in any of the readings provided on our website. By the way, regarding rules, let's come back to the fact that every functional dependency is a multivalued dependency. So we can use another Venn diagram. This is different than our previous one. We can list all of our multivalued dependencies here, and the functional dependencies are a subset of those. So what that tells us is if we ever have a rule that applies for multivalued dependencies here, that will cover the entire Venn diagram, and so that rule will apply for functional dependencies as well. So every rule for MVDs is also a rule for functional dependencies. On the other hand, if we have a rule that applies for functional dependencies, that rule does not necessarily have to apply to all multivalued dependencies because it might be specialized just to this portion of the Venn diagram. So one example of such a rule is the splitting rule. The splitting rule is a rule that applies to functional dependencies but does not always apply to multivalued dependencies. And again, you could work an example to convince yourself of that fact. Whew, so after all of that setup of multivalued dependencies, we're finally ready to talk about fourth normal form. The definition of fourth normal form looks very similar to the one for Boyce-Codd Normal Form. It says we take a relation and we take now a set of multivalued dependencies for that relation, and the relation is in fourth normal form if every non-trivial multivalued dependency has on its left-hand side a key. Remember, for functional dependencies, it looked exactly the same, except we had the functional dependency arrow here instead of multivalued dependencies. So let's see exactly what fourth normal form is telling us and why it's a good thing. So we have A, B, and rest as usual. And let's suppose that we have a non-trivial multivalued dependency. So that's telling us that if we have two tuples, T and U, and we'll put in some values for B and the rest, then we're going to have the combination of those as well. So that's kind of the proliferation of tuples we get when we squish independent facts in the same relation. But if the left side is a key, so if the A attributes are a key here, then we won't have those two tuples, and we'll never have to worry about the proliferation. Now remember that I said fourth normal form implies Boyce-Codd Normal Form, or if you prefer it in Venn diagram format, fourth normal form is stronger than Boyce-Codd Normal Form, and let's see why that's the case. If we have a fourth normal form and we want to show that we're in Boyce-Codd Normal Form, then we have to show that if we have a functional dependency, then the left-hand side A is a key. That would tell us we're in Boyce-Codd Normal Form. Well, if we have a functional dependency, we had a rule that tells us we also have the multivalued dependency, and then since we're in fourth normal form, we get that A is a key. So again, fourth normal form implies Boyce-Codd Normal Form. Now let's take a look at the decomposition of algorithm into fourth normal form. It's extremely similar to the BCNF decomposition algorithm. The input is a relation, a set of functional dependencies and multivalued dependencies, and we need to separate them because we use the functional dependencies to find keys. The output is a decomposition of R into good relations, in this case fourth normal form, and it's a good decomposition in the sense that reassembling the relations gives you back the original. As with Boyce-Codd Normal Form, we start by computing keys using the functional dependencies, and then we repeat the decomposition process until all of our relations are in fourth normal form. Just as with functional dependencies in BCNF, we pick a relation that has a violating dependency, in this case a multivalued dependency, and we split the relation based on that dependency. So we create one relation that has the attributes of the dependency and another relation that has the left-hand side of the dependency and the rest of the attributes. After that, we need to compute the functional dependencies for the decomposed relation and the multivalued dependencies for it, and then we can compute the keys. Now, finding these multivalued dependencies, this is actually a fairly complex process. Usually it's very intuitive, but I'm going to refer you to the readings to read about the algorithm itself. And in fact, it can be so complicated in the general case that some of the readings don't even provide the algorithm. But again, in general, it's very intuitive. Our first example is going to be very fast to do. As you remember, this example has one multi-valued dependency, Social Security number determines college name, multi-determines college name, and it has no keys other than all of the attributes. So obviously this is a violating multi-valued dependency, and so we decompose into two relations. We'll call them A1 and A2. The first one has the attributes of the multi-valued dependency, the Social Security number and the college name, and the second one has the left-hand side of the multi-valued dependency, as well as all the remaining attributes, which in this case is the hobby. These two decomposed relations actually have no FDs and no MVDs, so in that case we're definitely in fourth normal form, and we're done with the decomposition, and I think we can agree that this looks like a good schema for the data at hand. Our second example is quite a bit more complicated. Remember, in this example, we have that the Social Security number and college name functionally determine date. That means each student applies to each college on a specific date. And secondly, we assume that majors that were being applied for were independent of hobbies. So we have Social Security number, college name, and date. Multi-determines the major. And incidentally, that would mean it multi-determines the hobby too. Once again, we have no keys for the relation except for all attributes. So we have both a violating functional dependency in this case, and we have a violating multi-valued dependency. Let's use the multi-valued dependency for our first decomposition step. So we'll create A1 and A2. A1 will contain all the attributes of our multi-valued dependency, and then A2 will contain all the remaining attributes along with the left-hand side of our multi-valued dependency. And that turns out to be all of the attributes except the major. Now let's take a look at our decomposed relations and see what we have in terms of functional dependencies and multi-valued dependencies for them. So after the decomposition, we don't have any more multi-valued dependencies, but our functional dependency actually applies to both of the decomposed relations, and we still don't have a key on the left-hand side. So we need to decompose further based on the first functional dependency. So let's start by decomposing A1. We'll turn A1 into A3 and A4, and A3 will have the functional dependency, all three attributes, and then A4 will have the left side of the functional dependency and the remaining attributes, which in this case is the major. So now we're finished with A1, and we have a similar problem with A2. And so we decompose A2 similarly, although we'll discover that A3 is the same relation in the decomposition of A2 as we got with A1. So we actually only add one more relation now, which is A5, that contains the Social Security number and the college name from the left side of the functional dependency and the hobby, which is the remaining attribute. And then we cross out A2. Now, the only functional dependencies or multi-valued dependencies we have left do have a key on the left-hand side. I'll let you verify that for yourself. And these three relations are our final decomposition into fourth normal form, and I think you'll agree that this is a good design, again, for the data at hand. So let's wrap up this long unit on dependencies in normal forms with a quick summary. If we have a relation RABC, a functional dependency from A to B tells us that when we have the same A values, we have the same B values, and the Boyce-Codd Normal Form tells us to factor those attributes into their own relation so that we don't repeat that relationship over and over. For multi-valued dependencies, let's say we have the relation RABCD, and if we have the multi-valued dependency A multi-determines B, what that tells us is that we have every combination for a given A of B values and CD values. We called those rest earlier. And when we have that multiplicative effect of combinations, again, we take the A and B attributes and we put them in a separate relation so that we can separate out those facts from the independent fact of A and its CD values. Finally, in the design process, multi-valued dependencies are something we add to functional dependencies so they're stronger. So fourth normal form is a stronger property than Boyce-Codd Normal Form. Now, usually this design process works very well and is very intuitive for many schemas. I hope for the examples that I gave here, but there are actually a few shortcomings to using Boyce-Codd Normal Form or fourth normal form, and we'll cover those in the next video.